Alright, ladies and gents, so this video is about diffraction. What we're talking about today is another property of waves. So we're able to determine that light is a wave because it has a few it follows a few of the physical phenomena that waves follow. Okay, one of the things that waves do, first of all, is that they refract. Okay, which is that they change direction when they enter a new medium. So that's one thing that we see in terms of behavior of waves. And another thing that we see with behavior of waves is diffraction, which is the bending or spreading of the wave when it passes a barrier or passes through a small opening. Okay, we often call that an aperture. All right. So what happens when a wave spreads around a barrier or through an opening, which is really just a couple of barriers that's spreading around, is that it bends around the sides of it. Okay, so in the first example here we see around a barrier, all right, it's going to bend around the sides. The bigger the barrier compared to the wavelength, the smaller or less diffraction we will end up seeing. I'm going to show you some examples of this in class. If you actually go into your textbook, I believe it's 4.4 and 4.7, you'll see some images, all right, where depending on the size of the barrier, we see more or less noticeable diffraction. Actually, on page 260, I'm looking at some good examples. All right. So, how do we get noticeable diffraction, noticeable bending of a wave around the barrier? Well, what needs to happen is that the size of the opening, or the aperture, all right, should be approximately close to the size of the wavelength. Okay, this isn't exact. You know, oftentimes we'll see it off by a couple orders of magnitude, and we still get some diffraction. But in terms of these little ripple tanks, these water waves, it's more noticeable the closer the sizes. Okay, so well, how does this happen? Why is a wave bending around a barrier? We saw how waves can bend when they enter a new medium. And here I'm going to explain how waves, and at that time I used the lawnmower or the pushcart toy. I also explained it in terms of armies moving across a field into a new medium. But there's a better physical explanation for it. And you can actually use this explanation to explain refraction and diffraction. I'm going to use it here, though, to explain refraction. And Christian Huygens, okay, he basically said, you have a point source, S, right here, okay, emitting waves equally out in all directions. So I have my little line of waves coming out right here, okay, and what I have on top of this, I've drawn equally spaced points. Now, what he said is that every point on this wavefront can be considered its own source. So if we consider it its own source, we can draw circular wavefronts around each of these guys, all right? And what we're going to see is that as all of these circular wavefronts combine, if every point was considered to be its own its own source, that all those wavefronts, all those little circular wavefronts, what they do is they combine to make one total wavefront up here, okay? And so that's really how you can imagine a wave traveling out. So what happens, okay, is that this envelope, okay, of tiny wavelets is the new envelope, all right, and it's going to be tangent to all those little wavelets. So imagine again, we have a planar wavefront right here coming to a barrier, and consider each point equally spaced out here, all right, to help us to see this, is its own point source. Well, if that's the case, what we see here, okay, each of these little circular guys, all right, is the wavefront for each of those point sources, and if we draw the envelope encompassing all of them, we see that at the edges here we have this bending, okay, what appears to be a curved wavefront. And we do that again, and we keep doing that over and over, and what we see as it spreads out is that the wave ends up looking something like this, okay? So the reason why we don't have noticeable diffraction when the wavelength is much smaller than the aperture size or the barrier is because that amount of the wave bending around is going to be very weak, okay? It's only going to be a little bit of the actual wave energy coming through. So the amplitude is not going to be noticeable. But when you have it here, and there's only a few points gathered, you know, for it to spread out around, the energy is going to be spread out a bit more along those bent parts of the wave, okay, for its wavefront, all right? So that's why you see, you only notice it when the opening of the wavefront and the wavelength are about the same size. So why is there an interference pattern when light travels through a single slit? Okay, this is what we call single slit, single opening here, right? So different parts of the wave are going to interfere with itself as it spreads out. Okay, we actually have. Let me show you this here. When waves pass through, okay, we get that diffraction. We put a little screen right here. Say if this was for light, we end up with these an interference pattern. Okay, which actually what we see here is these different bands of light, dark and light. Bands, okay? And that's telling us that light is causing constructive and destructive interference, all right? So I actually have this image right here. This, I've changed the colors on this so it looks a little pixelated, okay? My goal here is to make sure that you can tell the differences between where we have constructive and destructive interference. And I'm not sure how easily you can see this on your screens. Probably not so much. I wonder if it's a little bit better here. Okay, but if you actually go to this website, the FET website, you see here that this is spread out, okay, kind of like the ripple tank that we saw. But there's going to be a bit more, and this next one is here, it's a little bit easier to see, all right, where on the screen, when the light hits the screen, we have this little intensity, all right, region where we see it's at a maximum, but within that, beyond that, we see it's darker here, and it's actually, so over here it's going to be darker, all right, and over here, so this is a dark fringe, and this is a bright fringe over here, and it's really hard to see. So actually, you know what? Go to this website, mess around with this simulation. You see here that I'm in the light tab, okay? You need to have one slit, okay, for this light to pass through, and mess with the frequency of the light, how big the slit is, how far the barrier is from the screen, okay? And look at where the patterns of the light, okay? The intensity, make sure you have the intensity graph showing. You want to be able to see how the light interferes with itself, okay? Again, looking inside the textbook too, have the textbook out with you when you're taking these notes. You'll see that we have light interfering with itself if we put a screen beyond a single slit barrier, all right? To observe the light diffraction, okay? So what we have here, okay, is light will interfere with itself when it diffracts through a barrier, okay? There's a lot there, all right? There's some features of this interference pattern that we get from the light that I'd like you to write down. We got a wide central maximum, okay, of the light as it passes through this barrier. We have a bright a wide central maximum and a bright central maximum. There we go. Those are the two characteristics. And the secondary maxima, okay, they're all approximately equally spaced apart. All right, so if we went through all these guys, all right, will be equally spaced and have equal widths. The intensities of them decreasing though as we get further and further away. All right. So again, what have I said here? This is pretty wild. All right, there's a lot going on. All right. First of all, waves bend around barriers. Okay. The reason that they bend around barriers is that we can consider each point in that wavefront to be its own source, all right? Those sources all create little circular wavefronts, and the envelope of those little circular wavefronts or wavelets, okay, is the new wavefront. So we get some bending around these barriers, and because each of these is its own point source, they're all going to interfere with each other, okay? And when they all interfere with each other, we get an interference pattern, points of constructive and destructive interference. We can see that with light, when we shine light through a small slit, okay, and we get these fringes of constructive interference, where it's bright, and destructive interference. Okay? So that's what's happening here, all right, with this diffraction. Now, you notice between these two images, okay, we have two different graphs. In this first image, all right, the slit is a bit more narrow than in the second image, okay? Now you'll notice between the two of these that there's this little bump here, okay, that's the secondary, it's not there, it's going to be right about here, there we go, okay. Those are the secondary maxima. Well, you'll notice the height of this first maxima is higher than the other one, okay, and that this first maxima is a bit wider, okay, in the narrow slit versus the wider slit. Okay, you can actually see that in the way that I've drawn it too, with the way of how it is spread out there. Okay, so there's some important characteristics here that I'd like you to note. All right, and we're going to draw them out here. And we're talking about the position of the first minima for a narrow slit versus a wide slit. Now, this x-axis here is the angular separation, all right, that we have in our interference pattern, all right? And the first, for a narrow slit, it's going to be pretty wide. All right, look something like this. Okay, for a wider slit, okay, we have a bit higher of a peak. Okay, so there we go. Again, not drawn incredibly well. Those should be equally spaced here. So let me just draw this. Let me draw that part right there. There we go. And I think there's something like that. And good. Okay. So you see here the characteristics. Okay. When the slit is wider, the central max is more intense. And the first minimum is closer, or has a smaller angular separation. All right, I'm going to talk about what this angular separation is here in a minute. All right. So for right now, this is just the introduction to diffraction, exactly what's happening when we have a wave hitting a barrier. Okay. Again, read the textbook. We will be discussing this more in class. The next slide is going to talk about, the next video, excuse me, is going to explain exactly how this happens. We're going to derive what is happening with diffraction, this bending of a wave, and this interference, okay, through a barrier, or through an opening or an aperture.